Average rate of change. Remember, calculus is the study of change. We're interested in learning about patterns regarding how functions change to see if we can use that to predict what may happen later on with that function. There's a lot of value in learning about the various ways that functions change. In mathematics, when we don't know how to do something, we often start with what we do know how to do and use that to adapt to figure out what we don't know how to do. So quickly, we're going to review something that we already know about how functions change. What we know at this point is how to measure the change of a linear function. So if we have a line, the way that we talk about how it changes is with a term called slope. So hopefully you remember hearing about the slope of a line. So the slope of a line tells us how much the dependent variable changes for every one unit that the independent variable changes. The slope of a line has a lot of ways to denote that that's what we're looking for. Oftentimes, you'll see slope of a line called m. M represents the slope. You may also have seen it as delta y over delta x, the change in y over change in x. Similarly, you may have seen something like y1 minus y2 divided by x1 minus x2. There's a lot of different ways There are a lot of ways that you may have seen slope represented, but all of them give us the same measure. Again, it tells us how much the dependent variable changes. So how much do we need to change in the y direction for every one unit that we change in the independent direction or the x direction? That's what the slope of the line tells us. So what we want to do is we want to take that idea and see if we can use it to talk about how curved functions change. So consider the following example. What if we want to talk about the change of a curved function? So we have a generic function here, f of x, and we want to find out a little bit about how much it changes between x equals 1 and x equals 3. So you can see that it's a curved line. If we could cut it out and straighten it out, we might have some ideas about that length, which is something we do in geometry. But we want to look at this in terms of the way it's shaped now with that curved bend. So what we can do is we can find out how much this function changes on average by using the slope of the line that connects the two x values that we're interested in. So you can see that represented with the red line over here on our function. So if we can find the slope of that line, it'll tell us how much the function changed from the point at x equals 1 to the point at x equals 3 on average. So what we're going to do is we're going to use what we know about the slope of the line to find the slope of this line. So again, we're going to do the change in y over change in x for x equals 1 to x equals 3. So remember, we're doing change in y over change in x. Now, as long as we're consistent with the order that we pick our x's, it doesn't actually matter if we do the 1 first or the 3 first, as long as when we put in the representative y value, it's in the same order that we choose our x's. I also want to remind you that one of the ways that we can represent the y value is to talk about f of the x value. So in this case, the way that I'm going to write the change in y over change in x is using functional notation. So I'm going to notate this as f of 3 minus f of 1 divided by 3 minus 1. So f of 3 represents the y value when x equals 3. So f of 3 here, I'm going to approximate. So that means that I'm going to estimate what the y value is because I don't have a clear answer. It doesn't look like it's at an exact integer, so I have to make a good educated guess about where that value is. So looking at this y value for f of 3, I'm going to approximate that that is approximately 1.3. Now, you may approximate it a little bit different. You may have said 1.25. You may have said 1.2, anything in that range is okay for an approximation. We want to get pretty close to what it is, but there's a little bit of room for error. So that's my f of 3 value, the y value that's connected to the 3. From that, I'm going to approximate f of 1. So that means I'm going to go up to where the 1 is, and again, I'm going to try to approximate what that y value is. So my best guess here, I'm going to call that 2.8. Again, you may approximate slightly different, but it should be relatively close to 2.8. So that's the change in y values, and then I'm going to divide that by the change in x, which was 3 minus 1. So again, order isn't necessarily important as long as you are consistent. I could have done f of 1 minus f of 3 divided by 1 minus 3, and I would end up with the same answer, but I have to be consistent with my x's and y's. So when I crunch this number in my calculator, I put that all in, and I get approximately negative 0.75. So negative 0.75 is the approximate slope of this line, which tells me that on average, my function changes by negative 0.75 in the y direction for every 1 unit that I move in the x direction. Now you can see that that's not true in every single place between 1 and 3. For instance, from 1 to 1.5, that function's increasing. So if I were to find the slope between 1 and 1.5, the slope would surely be positive. So it's important that we remember that when we do an average rate of change, it's talking about what's happening between the 2 points we picked, and not necessarily at every sub-interval between those points. However, it gives us a good idea about what's happening in terms of change of this function between 1 and 3 on average. We can calculate how much a function changes on average over an interval by computing the change in the dependent variable over the change in the independent variable by finding the slope of that line. So if we want to come up with a general formula to talk about the average rate of change, we need a way to represent the slope between any 2 points. We're going to use the points A and B here in our formula to talk about any 2 points that we're interested in looking between. So our formula here for average rate of change is going to be f of b minus f of a over b minus a. So again, when you're looking between 2 points, it doesn't actually matter how you pick your a and your b as long as you're consistent. So when you have an x value of a, the corresponding y value is f of a. And when you have an x value of b, the corresponding y value is f of b. So we're going to use this formula rather extensively throughout this course. The average rate of change is really important. And when you see the word average, that's a key indicator that we are going to be using this formula. So let's take a look at some examples of computing average rates of change. So let's start with the graphical representation of average rate of change. This is the same graph that I used in the previous example, and the red line represents the slope that we approximated in the first problem. When we looked between 1 and 3, we found the slope to be approximately negative 0.75. Now, if we're interested in looking between other points, we can apply the same formula. So let's look at this blue line. This blue line is interested in what's happening between x equals 0.5 and x equals 4.5. You can see those endpoints on the graph. And if you look at the corresponding x values, that's the interval where we're interested in. So if we're looking for the average rate of change, we need to do f of b minus f of a over b minus a. Because order only matters when connecting to the y value, I always use b for bigger. So my b value is always the bigger of the two x values. So I'm going to pick my b to be 4.5. So my formula is going to be f of 4.5 minus f of 0.5 divided by 4.5 minus 0.5. So again, I'm going to have to do a little approximating. I need to take each x value and approximate where the y value is. And again, it doesn't have to be perfect, but we should be relatively close to the same estimates. So at 4.5, if I go down and I look at the corresponding x value, that seems pretty close to -1. So I'm going to say that my y value is -1 minus. Now I go to 0.5 and I go up to the corresponding x value. That looks really close to 2. So I'm going to say that my y value is 2. And that's divided by 4.5 minus 0.5, or 4. So remember with negative numbers to be extra careful. -1 minus 2 is going to give me -3 over 4, or approximately -0.75. So the slope of this blue line is approximately -0.75. That's interesting because that's what we approximated our red line to be earlier. However, I noticed that when I look at the slope of these two lines, that I would expect them to be the same because these lines look relatively parallel, and parallel lines have the same slope. So this makes sense that my approximations would be really close for these two lines. So now let's consider what's happening between 0 and 2. The green line has an upward slope, so I'm expecting something different than the other two approximations. Additionally, I'm expecting the slope to be positive since my line goes in the upward direction. So again, I'm considering what's happening between x equals 0 and x equals 2. So that means my formula is going to look like f of 2 minus f of 0 divided by 2 minus 0. So f of 2 is another approximation. So I go to 2 and I go up to where it hits the function, and I need to approximate the corresponding y value. For me, I'm going to say that this is approximately 2.8 is my best guess. Hopefully, your approximation is something similar. My f of 0, if I look at where 0 hits, is really close to 1. So my y value there is going to be 1 divided by 2 minus 0, which is 2. So again, I'm going to crunch this number in my calculator, and when I put it all in, I get an approximation of 0.9. So again, I was expecting the slope to be positive, and it was, so that's good news. So here, the slope of this green line is approximately 0.9. So again, that tells me that on average, my function changes by 0.9 units in the y direction for every 1 unit in the x direction between 0 and 2, because those are the 2 points that I was considering here. Turns out that this line that we're using to approximate the average rate of change has a special name. When using a line to approximate the average rate of change between 2 points of a nonlinear function, that line is called the secant line. And the average rate of change is the slope of the secant line. So the slope of the secant line tells us the average rate of change, and the secant line connects 2 points of a nonlinear function. Note, the average rate of change of a linear function, or of a line, is just the slope of that line. And if it turns out that when you're computing average rates of change over a function, if they're all the same, then that function is linear, because the slope would be the same everywhere. Let's look at a few examples of how we can compute average rates of change in other ways that are not on graphs. So first, let's look at an example of a formula here that's y equals f of x equals x squared plus 3x minus 1. And let's try to find the average rate of change between x equals 1 and x equals 4. Since x equals 1 and x equals 4 is the interval where we want to calculate our average rate of change, that's our a and our b. I'm going to use 1 as my a and 4 as my b. Again, it doesn't actually matter how I pick my A and B as long as I'm consistent in the formula. So the formula again was f of b minus f of a over b minus a. By substituting in the values I have for this particular problem, that means I'm looking for f of 4 minus f of 1 divided by 4 minus 1. Now, since I don't have a graph here, I'm going to be finding my y values by plugging my x values into my function. So here when I plug in a 4, I'm going to have 4 squared plus 3 times 4 minus 1. So when I crunch that number, I'm going to get 27. So that's my y value up in the top. I also need to calculate f of 1. So again, I take 1 and I plug it back into my original function here. And then I crunch all the numbers. And so here, f of 1 is going to give me 3. So I go back and I plug that in for the y value, divided by. Now on the bottom, I have a 4 minus 1, which is 3. So I have 27 minus 3 divided by 3. And when I crunch that number, I get 8. So this function, on average, changes by 8 units, which is positive in the upward y direction, for every 1 unit that the function changes in the independent or x direction between x equals 1 and x equals 4. So the average rate of change here is 8, because again, we're talking about how much that function changes on average. We can also look at the average rate of change by using a table. So suppose the table below is continuous and gives the data of a population P in thousands measured in years T since 1970. One of the things that we need to address here is the fact that this function is a continuous function and the data reported on the table just gives us a snapshot. We talked before about what it means to be continuous versus discrete, and while tables are normally discrete, we can talk about information from a continuous function. So what that means here is that even though we don't know what's happening between the various t values, we know that they are connected in a continuous way. So if we want to talk about some of the various things on the table related to average rates of change, we want to go ahead and calculate that using the same formula. So there's 3 questions here regarding this table. The first is, what was the population in 1970? This particular question is important because we have to situate ourselves with what T represents. So T is in years since 1970. Then if we're talking about the population in 1970, that would correspond to T equals 0. So if we go to the data at T equals 0, we know that the population at that time is 60,000, because remember that the population is given in thousands. So whatever this population is representing, in 1970, there were 60,000 in this population. If we want to consider the average rate of change of this population, we need to look between 2 given points. So in question 2, we're asking what was the average rate of change between 1970 and 2000. So we need to figure out what the corresponding t values would be so we can use our table. So remember, t is in years since 1970, which means that 1970 corresponds to t equals 0. And 2000 is going to correspond to t equals 30, because it would have been 30 years since 1970. So that means when we plug this into our formula, that our A and our B are going to be 0 and 30. Up until this point, the way we've used our formula is with f of b minus f of a over b minus a, because we were using the generic f of x. Here our function is p of t, so we can adapt our formula just a little bit. We'll do p of 30 minus p of 0 over 30 minus 0. So instead of using f's, we can use p, since that's how this particular problem was defined. So we're going to take these and we're going to find the dependent value at 30. So the independent value of 30 gives us a dependent value of 85. The independent value of 0 gives us a dependent or y value of 60, all divided by 30 minus 0, which is 30. So now, if we crunch that number, we are going to approximate this. This is going to be 0.833 thousand. Now, why did I say this was an approximation? Because when you crunch this number, you get 0.833 repeating, and therefore, you need to round it off somewhere. So it becomes a slight approximation. So we get 0.833, and we have to remember that population is in thousands. So we have to add the word thousand to remember what our units are in this particular problem. So that means that this population changed by 0.833 thousand per year from 1970 to 2000 on average. Similarly, if we wanted to find the average rate of change between 1980 and 2010, we first need to figure out what our corresponding t values are. So 1980 is going to correspond to t equals 10, because that's 10 years after 1970. And t equals 2010 is going to give us t equals 40. So again, we can use the notation with the p here because we don't have an f of x, we have a p of t. So when we apply our formula here, we're going to have p of 40 minus p of 10 divided by 40 minus 10. So p of 40, we go to our table, we get the corresponding y value, which is 100. P of 10, we get the corresponding y value, which is 65, divided by 40 minus 10. 40 minus 10 is 30. So again, we're going to crunch that number, and we're going to get 1.167 approximately, and that's in thousands. So 1.167 thousand per year is what our population is changing on average between 1980 and 2010. So we can apply the formula to tables just like we could for graphs. Let's take one more crack at a graph to finish this up, and then we'll talk about some other real-world applications that this has. Consider the graph below. If we want to find the average rate of change from x equals 0 to x equals 4, we want to find the slope of the line that connects the function at 0 and x equals 4. I've signified this with the blue line. Remember, the name of that line is the secant line, and we're trying to find the slope of that secant line. So again, we're going to apply our formula here. We're going to do f of 4 minus f of 0 divided by 4 minus 0. And we're going to get those values from our graph. So f of 4, if you go up to where x equals 4 hits the graph, we come over and we find a corresponding y value of approximately 2. Then if we go to f equals 0, we can see it doesn't touch exactly at the origin, so it's a little bit above 0. So for my approximation, I'm going to call that 0.1. And then on the bottom, we're dividing by 4. Crunching that number, 2 minus 0.1 divided by 4 is going to give us 0.475. What that tells me that on average, this function is going to change by 0.475 in the dependent direction for every 1 unit I change in the independent direction on average.